So up until this point, we have been considering transmission lines that are perfectly efficient, meaning if I put 1 volt on one side of the transmission line, I can expect 1 volt to reach the other end, and that part was very straightforward. In practice, transmission lines are not like that. There is a small amount of loss within the transmission lines that come from 2 sources. The first is that the conductor of the transmission line is an imperfect conductor, which means that it may have a little bit of resistance to it. So when you have current flowing across a resistor, albeit a small resistor, you have some power that's being burned in that resistance, and that's power that's lost. And that power must reflect itself as a reduction in the voltage and the current of that propagating wave. The second place where we lose energy in propagating waves is in between the 2 conductors of a transmission line. For example, if you have a coaxial cable and you fill in the section in between the inner and outer conductors with some kind of a dielectric, that dielectric will have a little bit of conductivity to it. And so you basically have a resistor, albeit a big resistor, connecting the 2 conductors together. That resistor will have a little bit of current flowing between it when a voltage wave sweeps by, and that of course is burned, dissipated, and wasted power as well. So in this section, we're going to consider how that impacts the propagation of waves on transmission lines and how to take that into account properly. So we have 3 sections here. The first is just the basics of what we call lossy propagation. In part 2, we'll go through a numerical example, and in part 3, we'll talk about what's called dispersion along with attenuation. Attenuation is basically the gradual reduction in the amplitude of a wave. All right, so part 1, lossy propagation. I just want to remind you of the circuit model of the telegrapher's equations that we considered. And the upper diagram only shows the inductors and the capacitors that we considered each little branch of a transmission line as being a cascaded series of these inductors and capacitors. The LC combination slows down the wave and it forces it to propagate with a certain velocity. But the full telegrapher's equations also included this resistance term R. The resistor is basically assumed to be in series with the inductor. And this value G is basically going to be a resistor that connects the 2 together. The G is 1 over the resistance. It's called admittance. It has units of 1 over ohms. And that basically serves as a leakage current in between the 2 conductors. All right, so we're going to go through how this actually modifies our notion of waves propagating. All right, now to this point, if we're considering things in terms of a phasor, if we have a wave propagating in the positive direction on a transmission line, we can write this as V as a phasor as a function of Z equals a phasor value at 0 or at Z equals 0. I'm going to denote this with a 0 on the subscript here. So this is basically the value of the phasor at Z equals 0. And then what we do is for different positions of Z, we simply change the phase. And to change the phase, we multiply by e to the j times beta times Z. And this simply means that the phase is changing as you change your location, right? You'll get the same amplitude, just the phase is going to change. Because e to the minus j beta Z simply means rotate the phasor. Right? This rotates the phasor by an angle of beta Z. Right? Does not change the amplitude, right? So amplitude does not change. Okay, what we're going to do is we're going to introduce a new way to look at this. And for that, we're going to define something called gamma. Okay, if you take the telegrapher's equations and go through the solution with partial differential equations and come up with the general solution, here's what you're going to come up with. First, let's define this quantity that I'm going to call gamma. All right, gamma is going to be basically a more generalized version of beta, as we'll see soon. All right, so gamma is going to be equal to the square root of r plus j omega L times g plus j omega C. Okay? So basically, we're going to replace J beta, which only included the inductor and the capacitor, and we're going to instead replace J beta with a gamma, where gamma will have this formulation to it. Notice that if R and G are both 0, then this becomes gamma equals square root of j omega L times j omega C, which equals the square root of the two j's are going to multiply and become a minus 1. So minus omega squared LC. And so this is a j omega times the square root of LC, right? And that's and this is what we have been defining as beta, right? This also can be written as omega divided by the propagation velocity, or it's 2 pi over the wavelength, right? But gamma in this case equals j beta if there's no losses, right? If R equals G equals 0. All right. However, in general, if R and G are non-zero, then this gamma is going to have complex values, right? Which means gamma is going to be equal to the following. It's going to have that same imaginary part to it. We're going to call that J beta, but it's also going to have a value of alpha, right? And alpha is basically going to pop out whenever R or G are non-zero. All right, so now let's recast this wave propagation in those terms. So V as a function of Z will equal to V0 as a phasor positive times E to the minus J beta Z, that was the original. Now we're replacing J beta with this more generalized quantity called gamma. So I'm going to erase the J beta right here and just replace it with the gamma. All right, so minus gamma times Z. And because gamma can be divided up into a real and imaginary part, I'm going to actually write this as follows. This is the original phasor value times E to the minus alpha Z times E to the minus J beta Z. All right, so let's examine this for a second. That's the Z right there. Let's examine this for a second. And we can break this down into two pieces, right? This portion right here is the same propagating characteristic that we observed before, right? That's just the phasor is rotating, and so the phase is changing as you move along in the direction of the propagation. But this new term right here, alpha, has created this, right? E to the minus alpha Z. E to the minus alpha Z, since there's no J right there, is a simple exponential decline. So if we actually plot this, we're going to find something that looks like this. Right, here is V as a function of Z. And we're basically going to see the propagating part will sort of look like this, but the amplitude of this wave is going to be gradually decreasing. And it's going to be decreasing precisely according to an envelope, and the envelope is E to the minus alpha Z. All right, so the amplitude is simply exponentially attenuating, and alpha is going to tell us what that rate is. The way we get alpha is we go to this fuller definition of gamma, right? We plug in the values of R, L, G, and C, plug it in, and when you get that result, it's going to have a real part and it's going to have an imaginary part, right? The real part is going to be this number alpha, and that's going to define how quickly this attenuation happens. And the attenuation is, of course, happening in both directions, on both sides of this sinusoid. So let me just draw this in blue. And so this is a gradual reduction here. All right, so that's the basic idea, is all we need to do is we replace beta with gamma, and gamma will have a real imaginary portion to it. The imaginary portion of gamma will tell us the propagation, how the phase is changing with distance. And alpha is going to tell us how quickly the amplitude is attenuating with distance. All right, now let's talk about units for a second. Beta, we had called that the wave number. It has units of radians per meter, right? So if you walk forward by 1 meter, how much has the phase changed as a result of that? Radians, however, is kind of a fake unit in that it's a ratio of two things, right? Technically, radians is this ratio. I've got this angle right here, theta, in radians. This angle theta is the ratio of this arc length to the radius r, right? Theta equals s over r. So theta doesn't really have units to it when you're talking about radians. So this radians here is just kind of a placeholder to tell us that this is an angle, even though it's not really a real unit. Alpha is basically the attenuation number. And for that, we're going to have units of meters per meter. All right. Meters is also like a fake unit. It's a ratio, right? A single meter basically means that the amplitude has attenuated by a factor of 1 over e, right? So 1 over e is 1 meter. All right, and this is exponential. So 1 over e squared is 2 meters. Right, so each meter implies a 1 over e reduction in the amplitude. And so what this wave number alpha tells us is how many 1 over e reductions are we seeing every meter. And so then we know exactly how quickly the wave is attenuating, and it just follows e to the minus alpha z. All right, so that is all true in general. But let me just consider one case of a low loss and a high loss transmission line. All right, so there's a couple special cases. First is if alpha is much smaller than beta, which implies that gamma is mostly imaginary. All right, if that works out to be the case, then you're going to have a wave that basically looks the same as it would in a lossless case, right? It's a nice clean sinusoid, but it's gradually decreasing with distance. To the point where if you just look at one wavelength, you probably couldn't see the attenuation. But if you look at many wavelengths in a row, you will see a gradual reduction in the envelope. So this is what we're going to call the low loss case. And for this low loss case, we can approximate that alpha works out to be R, the resistance per unit length, over 2Z0 plus Z0, the intrinsic impedance, times G divided by 2. And the value of Z0 hasn't changed. It's the square root of L over C, the impedance per, the inductance per unit length divided by the capacitance per unit length. And also the propagation velocity has not really changed either. It's essentially equal to the 1 over the square root of LC. Right, in this case, beta also has a cleaner form. It works out to be omega over VP, or it's the same 2 pi over lambda. So beta hasn't really changed very much from what it was. But if you know what R and G are, you can pretty quickly figure out what alpha is, assuming that alpha is small compared to beta. And this is what we call the low loss case. So for that, there's simple analytical expression, a simple one for alpha and beta. All right, and this is called the low loss transmission line case. There is another potential situation where the losses dominate, right? Which is to say that the resistance is much greater than J omega L, or the admittance is much greater than j omega c. So going back to that definition of gamma, right, you can see in this term right here, if R is much greater than j omega L, we're going to get the resistance dominating over the inductance. And likewise, if G is much greater than j omega C, we're going to get the admittance dominating over the effect of the capacitance. And so we almost have a wave that's attenuating faster than it can propagate. And that's what we're going to call evanescent propagation. Or if you prefer, you can call it high loss. All right. In that scenario, it turns out that alpha equals beta, which equals R times the square root of the capacitance per unit length divided by twice the inductance per unit length. They both are equal to the same. All right. VP, by the way, the propagation velocity, this one's going to get a little bit wacky because VP is omega over beta, right? Since beta equals omega over the propagation velocity, just rearrange to get this. And since beta is now defined in the following way, this works out to be omega over R times the square root of C over 2L. So this is something pretty unusual that we are not used to until this point, where the propagation velocity is actually dependent on the frequency, right? So at 1 gigahertz or 2 gigahertz or 500 gigahertz, we're going to have different speeds or different propagation speeds along the transmission line. That's a new concept we haven't seen until this point. That's going to create something called distortion and dispersion, which we will cover in a later video. All right, but there are basically 3 ways that you can do this, or 2 ways. The first is you can always go back to this full formula of gamma. If you know the properties of the transmission line, and there are 4 of them, R, L, G, and C, plug them into this equation. And what you're going to get is going to have a real and imaginary part. The imaginary part will tell you how the phase changes with distance, and the real part will tell you how the amplitude of the wave changes with distance. If you happen to know that it's either low loss or high loss, then you can go straight to one of these 2 sets of formulas here, which will reproduce, which are basically special cases of the larger formula. But this will save you some time if you know for sure whether it's low loss or high loss. Most transmission lines, as you can imagine, are pretty low loss, as they would have to be for them to be useful. So any, say, coaxial cable, you're almost definitely going to be in this regime where alpha is pretty small compared to beta, and propagation is going to dominate over losses. But as you go higher and higher in frequency, you start to get increasing attenuation on a typical cable or on a typical trace on the transmission line. And we'll talk in the upcoming videos about why that's the case.